Okay, we are doing Introduction to Quantum Mechanics, 3rd edition by David Griffiths and Darrell Schroeter, and we are doing problem 1.4, and so here we go. So in problem 1.4, we are given this function, this wave function at time t equals 0, and we are asked in the first question to normalize that wave function, where we know that a and b are positive constants. So let's go to the board. We have our wave function. Here is our wave function. And so what does it mean to normalize the wave function? Well, to normalize the wave function, we learned that if you take the integral of the probability density function and you normalize it by setting that equal to 1, that's how you normalize the wave function. And you have to multiply, that's how you normalize the wave function. And you have to multiply the probability density function with some sort of complex constant a. And so that's why we're multiplying it by a. And now we basically just solve for a in terms of the values we do know, little a and little b, which are just constants. And that is basically normalizing the wave function. So just rewriting here. So again, we're normalizing it to equal to 1, and a is a complex constant, but we can just pull that out. And we know that the wave function has values between 0 and b, but is 0 at less than 0 or greater than b, as we can see here. See 0 and a and b there's a function, otherwise it's 0. So I've simplified the integral instead of between negative infinity to infinity to just be between 0 and b. Okay, and so now we need to solve this integral. So we got to split the integral up because there are two parts to the wave function. There's the part of the wave function that is between 0 and a, and that is x divided by a. And then we take the probability density function, which is simply the wave function times its complex conjugate. Because there are no imaginary numbers here, it's just the wave function itself squared. So that's why I got x squared divided by a squared between 0 and a. And then the other part of the integral is for the wave function between a and b. And again, that's the probability density function is that wave function times its complex conjugate. Again, no imaginary numbers, so that's simply the wave function squared. So here, this is the wave function between a and b, and I am just squaring that to get this value. So there is that, and then now we basically just solve this and set this whole thing equal to 1, and then solve for a in terms of solve for capital A in terms of little a and little b. So I'll just sort of scroll through the steps I did here to solve this integral. And you can pause at any point in this video, and I definitely skipped a couple of steps, so you'll have to do this on your own, and also make sure that I didn't make a mistake in my math. There we go. And then from there, after solving the integral, the definite integrals, we are now just doing algebra and simplifying. Simplifying, expanding, factoring, trying to eliminate terms, like terms. And then remember, we set this equal to 1. That's how we normalize it. And then we solve for a. And that is the answer I get for capital A. And that is how to normalize the wave function. All right? Now the next thing is asking, now part B is asking us to sketch the wave function at time equals 0 as a function of x. So we're just going to sketch it. So we're going to draw our graph. And we know there are two parts to the wave function. There's the part between 0 and a, and that wave function is x divided by a, which is a linear function with a slope of 1 over a. And as x approaches a, the function approaches the value 1. So that's why I have a line here, because it's a linear function with slope 1 over a, which is positive slope, and then it hits 1. And then between a and b, the function is b minus x divided by b minus a. Again, that's another linear function with the slope being negative 1 over b minus a negative slope. And as x approaches b, the function approaches 0. As x approaches b, the function approaches 0. So that's why it's going back down, and then at b, it's 0. So there is the sketch of the wave function, and that up there is just the this is the y-intercept of the linear function that is the wave function between a and b. So, all right. I hope that helped. Oh, by the way, you can use this sketch to easily figure out C and E, and it will help out with D as well. Because imagine imagine you want to figure out what's the most likely location that the particle will be at, what value of x. And it's very easy to see that we can see that it will most likely be where x equals a. That's when the function approaches 1. Now, now officially what you're supposed to do is you do the probability density function and find the expectation value of x. So C and E are essentially the same question. But we are not expected to solve it mathematically. We're supposed to intuitively, with this graph, figure out that the expectation value and the most likely location of particle is at x equals a. All right, I hope that helped, and tune in for hopefully more problems. Thank you. Bye.